All right, welcome to The Explainer. Today we're diving into the story of a really fascinating idea called single point theory. It's the biography of a theory, really, how a simple question has grown and evolved to take on some of the biggest puzzles in physics. So let's track its journey from a what-if moment to a whole new way of looking at reality.
You know the standard story, right? The Big Bang, everything exploding from a single infinitely dense point. But single point theory, or SPT, comes at it from a totally different angle. It asks, what if that point didn't explode? What if it just started to pulse, to tick, generating reality frame by frame at a speed that's almost impossible to imagine? It's a huge shift in thinking. So where does one simple pulse even take us? Okay, so section 1, a point in motion. This is really where it all begins, with a philosophical question. Instead of a static, one-and-done singularity, what if the foundation of everything is a dynamic, unending process? A single point just constantly in motion. At the absolute core of SPT, you've got this thing called the primary cycle. Think of it like the universe's ultimate refresh rate, or its fundamental clock tick. It's a pulse beating over 10 to the 43 times every single second. That number is just mind-boggling. It's not just fast, it's supposed to be the actual clockwork of existence, building every single moment of our reality from the ground up. So that's the pulse. But how on earth do you build a universe from just a pulse? That question brings us to section 2, reality as a vortex. This is where we go from a simple ticking clock to the rich, complex reality all around us. So the big idea here is that space isn't empty. Not at all. It's what the theory calls a process field. And that equation you see, it's just a simple way to describe this field. The A part, the amplitude, is basically the energy density. You know, how much juice is in any given spot. And the phi part, the phase, is like the local rhythm, the direction of the flow. So yeah, space isn't a void. It's more like a crazy, turbulent, energetic ocean. Right, so if reality is this big, energetic ocean, what about, well, us? What about particles? In the standard view, particles are just little points floating in space. But SPT says, no way. Particles aren't in the field, they are the field. They're like these stable, self-sustaining whirlpools, vortices, and all their properties, mass, charge, you name it, they just emerge from the dynamics of how that vortex is spinning and structured. And of course, not all these whirlpools are the same. You've got these tiny flickers, what we call virtual particles, which are basically failed attempts to form a stable vortex. Then you get something like an electron. That's a really stable little whirlpool with a simple, single twist. But the proton, man, the proton is the king of stability. It's modeled as this incredibly tough, triple-wound knot of smaller quark vortices. It is exceptionally difficult to unravel, and that's why matter, actually sticks around. All right, this is a pretty cool story, right? But the big question is, does it actually work? Can it do real physics? That's section 3. Testing the theory. Because, every cool idea has to eventually face the music. It has to match what we actually see in the universe. So what about gravity? This is a huge one, and SPT's answer is pretty wild. It says gravity isn't a fundamental force at all. It's just an effect. The idea is that matter, being a big concentration of energy, creates a slope in the field's amplitude. And what we feel as gravity is just the natural tendency to move along that slope. And the really cool part, when you do the math and demand that it matches Newton's law for planets and stuff, it works, but only if the theory's own constants are tied directly to g, the universal gravitational constant. It all just clicks into place. But here is where it gets really exciting. A good theory doesn't just explain what we already know. It predicts something new. And this one does. Because a particle is a vortex with a real size, not an infinitely small point, the model predicts that if you get super, super close, we're talking nanometer scales, gravity should actually get a little bit weaker or softer than Newton's law says. And that's a concrete prediction you can actually go out and test. That's how you know you're doing real science. Okay, but that prediction raises a massive question, right? We have some incredibly precise experiments. If these effects are real, why haven't we seen them yet? This leads us to the real heart of the story, section 4. The evolving wall. This is the breakthrough that literally saved the entire theory. I mean, seriously, this is the kind of question that can kill a new theory in its crib. For decades, our experiments have confirmed standard quantum physics to a ridiculous number of decimal places. So where's the wiggle room? Where are these strange new effects SPT is talking about? Well, the answer turned out to be way more subtle and clever than anyone expected. The breakthrough was discovering this hidden scaling law. Now, don't let the symbols scare you. EC is just the energy where you'd expect to see the new physics pop up. And E probe is the energy of the experiment you're using to look for it. The huge insight was that EC isn't some fixed target. No, it actually changes depending on how hard you look, scaling up pretty fast, to the power of 1.5, in fact. So what does that actually mean in plain English? A great way to think about it is vacuum stiffness. It's like the fabric of reality resists being disturbed. The harder you poke it, the more energy you use in your probe, the stiffer it becomes in response. So every time we build a more powerful experiment to find this new physics, the goalposts literally move. The universe just gets stiffer and pushes the evidence just out of our reach. It's a cosmic game of hide and seek. And look at what this means in practice. It's wild. If you're probing at a low energy, say around 13 electron volts, the new physics just has to be hiding somewhere above 89 mega electron volts, okay? But just crank up your probe a little bit to 37 eV, and boom, that wall jumps all the way to over 400 MeV. You see what's happening? The theory isn't just getting lucky and dodging falsification, it's actively building this curved wall that gets steeper the harder you push. And that explains exactly why we've missed it for so long. Discovering this scaling law was a total game changer. It suddenly made sense why all those ultra-precise experiments came up empty. It gave researchers a map, telling them exactly where the boundaries of new physics might lie. And for physicists, this kind of behavior is a really big deal. It has a fancy name, a renormalization group flow, but all that means is that a theory's rules can shift depending on the scale you're looking at it. That's a sign of a really mature, self-consistent model. It was the key that unified the whole theory. So now, with this powerful new understanding, the theory was ready to start tackling even bigger challenges. Which brings us to our final section, from stars to observers. This is where we see just how far this maturing theory can reach. Let's think about the sun for a second. We all know Einstein's famous equation, E equals mc squared, right? Mass is converted into energy. But what does that physically mean? Well, SPT gives us this beautiful picture. The tiny bit of mass that's lost when hydrogen fuses into helium doesn't just vanish. It's a direct conversion into the energy of that underlying process field. The vortices, the particles, are literally reconfiguring themselves into a more stable, lower energy pattern. And the difference is the light and heat that powers our solar system. But look, progress in science is never a clean, straight line. The theory hit another huge roadblock. Early versions predicted that a certain energy level in heavy atoms, it's called the Lamb shift, should be a little bit off from what we expected. But the experiments showed, nope, it was exactly where the standard model said it would be. This was a make-or-break moment. Was the theory just wrong, or was a piece of the puzzle still missing? And here's the conflict in black and white. The standard theory, QED, makes a prediction that scales a certain way, and it matches the data perfectly. The first draft of the SPT model predicted something different, and it was just plain wrong. It didn't match the data. That's a serious problem you can't just wish away. The solution was another profound shift in thinking. The theory was forced to mature. It had to realize that the observer isn't separate from the experiment. We're not just looking at the universe from the outside, we are part of it. We're part of one giant interconnected interference pattern. So a measurement isn't a passive look. It's an active interference between us and the thing we're measuring. And it turns out for these heavy atoms, that very active interference naturally suppresses the exact deviation the early model predicted. The conflict vanished, not because the theory was wrong, but because it wasn't yet complete. So where do we go from here? Well, this story is far from over. This refined theory now points to new, very specific tests. Things like muonic hydrogen, where a heavier particle should actually amplify SPT's effects and make them easier to spot. Or the model now predicts tiny, measurable deviations for medium-heavy atoms like iron, deviations distinct from what QED predicts. And of course, in heavy ion collisions, we can hunt for unique signs of that stiffened vacuum. The theory is very much on the line, ready to be tested. And that brings us to the end of this biography, at least for now. The story of single-point theory leaves us with this powerful idea to chew on. Maybe the universe isn't a collection of separate little things, but one single, intricate interference pattern. One where scale itself isn't fundamental, but is simply woven from the phase and the rhythm of an underlying universal pulse.